time to Delhi, but the first time to St. Stephen's College, and I really appreciate it. And of course, I'm greatly honored to be here for this first lecture. Now I have to understand how to make this computer work. I have no idea how to advance the slides. Over there. Okay, good. Great. And of course, I had the wonderful opportunity of knowing Charu and Ram and that pretty, where are you pretty? There, okay. Long ago, and I was, of course, immediately charmed by Charu and also by the brilliance of her mind. There's much more that could be said. She was able to overcome obstacles and get a really an appointment, and she just left us much too soon, I'm sorry to say. I'm going to be speaking to you about mass spectrometry imaging in the service of human health. And anybody who wants a copy of what I'm saying, here's my email address, just email me. So you can relax about this. Let's begin. I'm going to be particularly interested in using the technique of mass spectrometry. Those people who know mass spectrometry? Not everyone. Not everyone. So just to make sure you understand what this is. The idea of mass spectrometry is that you can make ions move in a vacuum and apply various external fields, electric fields, magnetic fields, which will make their path go depending upon what charge they have and what mass they have. So the whole name mass spectrometry is a misnomer. It should be called mass to charge spectrometry. That's what you measure, the mass to charge ratio of what we're seeing. And the person who, in my mind, first started this process was J.J. Thomson. And Thomson got the Nobel Prize in Physics in 1905 for the electron. And Thomson was using something called a Crookes tube, in which you'd make a discharge, and indeed you could bend it by applying a magnetic field. Any of you can see the same phenomenon if you start to bring a magnet up to your TV set. But I warn you, don't do this because you'll magnetize your TV set and your picture will be distorted ever after. So be careful. But you can do this and you can see the effect. He had a student by the name of Francis W. Aston, who started his work before World War I, got interrupted. Okay, I'd like to turn that one off, actually, if you don't mind, so people can see better. Okay, there, excellent. Okay. And Aston made a discovery as a graduate student that would go on to lead him when he got his PhD after World War I in 1922 in chemistry, because he made a discharge in neon. He made neon ions, and he found that the neon ions split into two when he applied a magnetic field and bent them. And he was smart enough to figure out they had different masses, and this was the beginning of isotopes. He discovered isotopes. The elements had isotopes, and there's the same number of protons, that's what gives an element its name, right? But different numbers of neutrons. And so he was able to learn about this, and he actually found hundreds of different isotopes, and it tremendously advanced our understanding of chemistry. Here's actually a replica of Thomson's third mass spectrometer. And you might think, oh, mass spectrometry must have been something immediately that would change chemistry. If you think back, how did you go from alchemy to chemistry? What was the difference? What made the difference? And it was when people could actually make measurements. People could start to measure pressure, measure volume, measure weight, weighing things. And of course, there's no better way to weigh things than a mass spectrometer, as it turns out. But people didn't have it. In fact, it would turn out, even though this is 1903, and I'm going to read you this quote in a moment, mass spectrometry really did not take off until maybe the late 1950s. Why? Why was it so slow? And the answer is because people could not routinely make a good vacuum. It would take that long to make a vacuum. And without having a good vacuum, you'd have collisions with gases, and you couldn't apply the laws of physics and with great accuracy to find out what that mass-to-charge ratio was. And since then, I think almost no chemistry department doesn't have a mass spectrometer. It's become that powerful in terms of its use. So now we'll get a sense of what a mass spectrometer is. And I now want to read you what Thompson wrote. I feel sure that there are many problems in chemistry which could be solved with far greater ease by this, that's his mass spectrometer, than any other method. The method requires an infinitesimal amount of material and does not require this to be specially purified. Very interesting. We're going to take advantage of this. Now I'm going to jump ahead to the next big advance in mass spectrometry in my mind. I'm sorry I have to come here to run the computer. And this is due to John Fenn, somebody I got to know, who was a professor at Yale University. And Fenn did something called electrospray ionization, or ESI. Do you have a device that I can use for the computer? You'll do it for me? Oh, I appreciate it. I really appreciate that. That's excellent. If you do that, and then I have a stick, something I know where to put it. I know how to put that in. Thank you. That is excellent. That allows me to be free from the computer. And I appreciate that. Oh, okay. So what this thing, ESI, electrospray ionization, what was so special about this? Let me show you first of all how it works. You take a liquid and you squirt it out of something like a needle, okay? I speak American English, so I call it a capillary. You would otherwise know it as a capillary, right? I'm sorry, I'm not able to do British English. You can, I can't. Anyways, this is droplets. The droplets have charge, and the picture people had was the charges, as they drop, would evaporate, would get closer together, and you get a Coulomb explosion, fission of the droplets, and ultimately you have bare ions that would go into the mass spectrometer. I think actually this isn't as true as people first think. I think a lot of it comes from heating the droplet when it goes here and evaporating it inside the mass spectrometer. But the beauty of this is it introduced ions at atmospheric pressure and room temperature into the mass spectrometer. Prior to this, people always made ions by electron impact or something like that inside the mass spectrometer in the vacuum. Okay? Now, let's make this go. And I want to show you John Fenn and the quote of what he said at Stockholm in his Nobel Prize address. He said that his technique, this is how to make elephants fly. And here he is, you know, representing an elephant. What elephant is he talking about? He's talking about primarily biomolecules or polymers. Because why? You can sit down now. Sorry. Why? Because prior to this, people would do electron impact and they'd shatter into a bunch of pieces and no one knew what they were. Okay? You couldn't learn much from this. Whereas this way, the intact molecule would go into the mass spectrometer, often with more than one charge if it's large. You're not used to, small molecules can only hold one charge because of Coulomb's law, right? You get two charges, get too close together. Large molecules can hold many charges, or can't. Anyways, I don't want to dwell on this, but we have an idea of where this topic comes from. And another advance is due to my friend, Professor Graham Cooks, and he, at Purdue University, and he uses a variation of this ambient ionization mass spectrometry called desorption electrospray ionization, or DESI. Okay, how does this work? You send in a droplet on some surface, okay, and the droplet makes a splash of smaller droplets. And some of those droplets go into the inlet of the mass spectrometer. Actually, what do you pick? you pick some droplet that dissolves something on the surface, okay? And you have to pick the right thing. And even wets the surface, so the next droplet may not just be the first droplet, the second droplet can take it away. And you can see that this now comes around 2007, 2008. So it's only like, 9 years old or so that we're talking about this technique. It starts at Desi. He had a student who was tremendous, and she still is. She came as a postdoc in my lab, and she's now an assistant professor at the University of Texas at Austin with her own program. And this is Livia Eberlin. I want to show you a particular collaboration that I'm very, very special. It was without this collaboration that what I tell you could not have happened. It can't be done alone. And look at the people involved. In chemistry is Livia, okay? We need statistics. That's Rob Tucciarani, who's a professor of statistics at Stanford. We need a person who can read tissue. And here's Professor Terry Longacre. She's an outstanding pathologist, and she has some other people helping her. Okay, and then we need a person who can do surgery. And the person who's been doing the surgery is this man, George Poltsides, who cuts people up 3 days a week. This is not your normal combination of people who work together. Okay, but it's very much needed to make this happen. I'm going to tell you about it. So what am I addressing? Can we improve margin assessment during surgery for, in this case, GI cancers? That stands for gastrointestinal tract, inside us. I'm going to go over this, and I hope this is hopefully particularly relevant as a way to start this memorial lecture series. Molecular assessment of cancer surgical margins. Now, what's meant by margin? Well, people take a cut, and they try to figure out at the edge of the cut, that's the margin. Whether, did they get it all or not? That's a serious question. And I better start by telling you that surgery is the most common treatment of solid cancers. If you have a solid cancer, the best thing you can do is cut it out, okay? Generally, you can do well, depends where the cancer is. If you can get it early enough, you can cut it out, okay? But here's the situation. Positive margins, meaning if you have cancer cells left behind, you have increased local recurrence and decreased overall survival. Complete surgical resection's a good thing, prolonged disease-free survival. Okay? Now, in practice, how do you do this? The delineation of the resection margins is actually difficult and variable. And I'm going to try to show you why. What are the techniques that people use? What they do is they take a slice and they hand it to the pathologist. Pathologist freezes it. Pathologist stains it with some chemicals. Then looks at it underneath a microscope and tells the surgeon more to the left. Okay? Or keep going. Or stop. You're now finished. It's very important, right? That's how it's done. I hope, I don't know, any of you who've had your own operations about tumors, or know people who've had operations about tumors, those operations go on easily 4 hours or longer. Am I right? Is it because the surgeon can't cut fast enough? No. It's because every cut requires somewhere between 20 and 30 minutes to make a reading to know what to do next. It's really bad, you see. Okay? And now I got even worse news for you. I'm going to tell you something that hospitals don't tell you in general. They don't want you to know. The results can be unreliable in up to 30% of patients undergoing resection for pancreatic or gastric cancer during surgery. That means 2/3 great, 1/3 leave with still cancer inside. That's awful, right? And then what happens is that they can later on, by looking at what they've cut and doing things that involve PCR and and immunochemistry. They can tell you in a few more days what's happened, and that you now need radiation therapy or chemotherapy or both, or you need to have another operation. That's what goes on in these situations. And this is what I'm trying to address here. Okay. We could go over the nature of gastric cancers. Here you can see the esophagus and the stomach and so forth. You have there are various types of cancer tissue, normal tissue, there are mucosa and submucosa, which are named epithelial and stroma, and so forth. Okay. It's the fourth most common cancer worldwide, is these type of cancers. And it's the second most common cause of cancer death worldwide. Lung cancer is the first. Just giving you a sense of what's happening. Okay? And now I want to concentrate on lipids. Okay? What are lipids? Lipids are these fatty acids, all right? You remember lipid molecules? I don't know if you've come across it in some course or not. These are molecules that they tend to have a phospho group on them, and they have two carbon chains that come off and a body, okay? Fine. Cancer cells reprogram their metabolic pathways to make lipids. Why? Because they use these lipids to build cell walls and to proliferate. So cancers hijack the machinery and make this happen, make lots more lipids. And now let's take a look. There's something called the Warburg effect. Cancer cells take up and utilize much more glucose than normal cells, and they make much more lipids. Okay? This man, Otto Warburg, who won the Nobel Prize in Medicine in 1931, realized this by observation and came up with a theory of cancer. His theory was, it is a sickness of the mitochondria. This is his idea. This is in the early 1930s that he's talking about this, or end of 1920. People did not understand genetics at that time. We know now that's completely wrong. Okay, it's okay. That's how science advances. We know now that cancer comes from a genetic mutation, okay, of some sort or another. Appreciate what's happening. Okay, fine. But in the last decade, the altered lipid metabolism has been increasingly recognized as a common property of malignant cells. So we're going to be looking to start with at lipids. Now, to look at lipids, I have to be able to get them into my mass spectrometer and knock out some more chemistry. I need something which will dissolve lipids. And I use acetonitrile and dimethylformamide in about a 1-to-1 mixture to make the droplets. That will pick up grease. That's what we're talking about. These are greasy molecules, right? Fine. Okay. And here's the setup. Now, I want to really get this setup across. This is in the air. This is in my lab. Okay.